In this lecture, we're going to talk about the periodic table and Lewis dot structures. Now we're really going to talk about how the periodic table is organized. All of the elements can fall into one of the four major categories. 1. Metals. 2. Non-metals. 3. Metalloids. And finally, noble gases. On the periodic table, you will notice that there is a stair-step line between barium, silicon, arsenic, tellurium, and polonium. And this is a special staircase line because this indicates where things lie on the periodic table. So, the first major categories are the metals and are typically solids in room temperature, good conductors of heat and electricity, and are generally shiny, ductile, and malleable. These are generally found to the left of the staircase. So here's the periodic table, and I said the metals are to the left of the staircase. So all the elements that are to the left of the staircase are considered metals. The next major category are the nonmetals, and they are typically solids, liquids, or gases at room temperature, but they're not very good at conducting heat or electricity and are very brittle and not lustrous. They are typically found to the right of the stair-step line. The nonmetals are to the right of the staircase. The semi-metals or metalloids are the ones that are bordering the stair-step line except for aluminum and have the characteristics of both metal and non-metal. So they're called semiconductors because they can only conduct heat, electricity at very high or very low temperatures. So the metalloids or semi-metals are the elements that are on the staircase line except for aluminum and polonium. So there we are. Those are the elements that are semi-metals. The fourth major category are the noble gases, and they comprise the very last column in the periodic table and are all gases. That's why they're called noble gases. And they have a very full valence shell, so their s and p orbitals are completely full and are very unreactive because they are happy. So the noble gases are the 18th column on the periodic table right here. So quick overview, metals are all the elements to the left of the staircase. All the elements that are on the staircase are the semi-metals or metalloids, and these are the non-metals to the right of the staircase. And finally, the noble gases are the 18th column. These that are down in the F block are also considered part of the metals, so that's why it is green. In addition to the four major categories, we're going to learn about the family names. Alkali metals are the first group and have one valence electron. Again, if you notice, they all have S1, 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 S1. So they all have a valence electron of 1 because of NS1. And they are very reactive with water and produce alkaline solutions. So things that are basic, that's why their name is alkaline. The second group are known as the alkaline earth metal. This time they have two valence electrons, as you notice. This has 2s2, 3s2, 4s2, 5s2. So these have all the same electron configuration, ns2, and they have two valence electrons. These also react with water to produce alkaline solutions, but are not as violent as alkaline metals. Then we have the transition metals. The transition metals exist in the D block. So these are all in the D block, and they are good conductors of electricity and are very lustrous. They are less reactive than alkali and alkaline earth metals. They don't form compounds and typically exist as free elements in nature, so that's why we have gold, silver, zinc, copper on their own. Then there are the lanthanides. The lanthanides exist in the F block. They are the first row of the F block. On top of being the first row of the F block, lanthanides are shiny metals and have the similar reactivities as the metals in group 2 or the alkaline earth metals. Next are the actinides, which are the second row of the F block. And actinides are typically radioactive. The first four, thorium all the way down to neptunium, are naturally occurring, and all others have been created artificially in a lab. And so that's what is so special about actinides. The next family we're going to talk about are halogens. Halogens are the 17th group, and if you notice their electron configurations, it's S2, P5, 3s2, 3p5, 4s2, 4p5. They all have an electron configuration of ns2, np5, and this tells us that they have 7 valence electrons. And typically, halogens pair very nicely because they have 7 valence electrons. In order to fulfill the octet rule, they need to gain an electron. So they will pair nicely with alkali metal groups because those have 1 valence electron and will want to lose their 1 electron. And the final family are the noble gases. It is the last group. If you notice, they all have 8 valence electrons except for helium, which has 2 valence electrons. And in a chemical reactions, these will neither gain or lose because they are already happy with the octet rule. And so they typically do not react. And this means that they are inert. They do not have chemical reactions. So as a quick summary, we're going to go ahead and talk about fill in the table in your notes. Group 1 are known as the alkali metals, and they have electron configuration of ns1. N being the energy level it's in, or the row period. It has 1 valence electron. Number 2 are alkali earth metals, and they all have 2 valence electrons and have an electron configuration of ns2. Groups 3 to 12 are known as the transition metals, and valence configuration and valence electrons are going to vary, so go ahead and leave that blank or X, or just put it varies. Group 13, 14, 15, 16 don't have special names, so we're just going to call them by the element on the first row. Boron family, and that has an electron configuration or valence electron configuration of ns2 and p1 and has 3 valence electrons. Next one are carbon family. It has electron configuration of ns2 and p2, has 4 valence electrons. Group 15 is nitrogen family. It has a valence electron configuration of ns2 and p3 and has 5 valence electrons. Group 16 are known as the oxygen family. It has the electron configuration for the valence shell as ns2 and p4 and 6 valence electrons. Group 17 again has a special name. It has halogens, and it has a valence configuration of ns2 and p5, 7 valence electrons. Group 18, the final one, are the noble gases, and they have a valence electron configuration of ns2 and p6 and have 8 valence electrons. Alright, if we look at group 1, all of them have 1 valence electron, so here's the structure. So this dot right here would be the element symbol, and it has 1 valence electron. Group 2 has 2 valence electrons. Group 13 has 1, 2, 3 valence electrons. Group 14, 1, 2, 3, 4 valence electrons. Group 15 has 1, 2, 3, 4, 5 valence electrons. 16 has 1, 2, 3, 4, 5, 6 valence electrons. 17 have 1, 2, 3, 4, 5, 6, 7 valence electrons. And finally, 8th have all 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So let's go ahead and quickly review valence electrons. First, we have to remember what constitutes the Bohr model. Now, the Bohr model has a nucleus and then has electron shells. These shells are the energy levels. Now, the valence shell is the outermost shell, so the highest energy level. So in this case, this Bohr model has 1, 2, 3 energy levels, so the third energy level will be our valence shell. Now, the electrons that exist in the outermost shell are known as valence electrons because they're in the valence shell. In this example, there are 3 valence electrons. Now, atoms will either gain, lose, or share electrons in order to have a full valence shell. And in order to have a full valence shell, you must have 8 valence electrons. So if we look at this example, this has 3 valence electrons. Now, we have to consider, is this going to gain or lose? And when we think about it, is it easier to lose 3 in order for us to have 8 valence electrons, which are in the lower outermost shell? Or is it easier for us to gain 5 more electrons? And in this case, it would probably be easier to lose the 3 electrons and end up having 1 energy level less. And so our valence shell will be in the second energy level. Now, each shell can contain only a certain amount of electrons, and so the first energy level, n equals 1, can only have 2 valence electrons. The next energy level, which is n equals 2, can have a maximum of 8 valence electrons. The third energy level has a maximum of 18 valence electrons. And the fourth energy level has a maximum of 32 valence electrons. So just as long as you remember how the maximum amount, you should be okay with the valence electrons. Now we're going to talk about valence and electrons and how to do Lewis dot structures. So we're going to do a couple of exercises before you go ahead and finish your packet. Now, I have to explain right now that when you do Lewis dot structures, there are 2 ways that you can do them. So let's go ahead and do a couple of examples. The first one, let's go ahead and do boron. Boron has 3 valence electrons. And so if we have 3 valence electrons, we can go ahead and do the Lewis structure. With the Lewis structure, you always have to have the element symbol in the center. So boron's element symbol is B. And so it has 3 valence electrons. We're going to go ahead and represent a valence electron by just simply a dot. Since there are 3 valence electrons, the first way that I like to do it and would encourage a majority of you to do is what I like to call the ring around a rosy. And so you would put 1 electron on the top, 1 electron on the side, and 1 electron on the bottom. Now, this is one way. The other accepted way would be if I had the boron, and you can put B on top of B 2 electrons, and then go ahead and start the ring around the rosy. Now, since this is acceptable, and we haven't gone over this, but the reason why this one is acceptable, people consider that you are filling it as if you were doing the orbital diagrams, and this is represented by the s orbital, and these are the 3 p orbitals. So this version is really acceptable. The only reason why I encourage to do this, where you do the ring around the rosy, is it plays a bigger role when we do bonding. So you can do either way, but when we start doing bonding, we're going to focus more on this type of Lewis dot structure. Okay, so let's do a couple more examples. So if we look at nitrogen, okay, it has 5 valence electrons. If we were to do the Lewis dot structure for this, we would go ahead and start with the N in the middle and do the ring around the rosy. So 1, 2, 3, 4, and now I start pairing up with 5. Now let's do fluorine. Fluorine has 7 valence electron. Again, we start with the element symbol in the center, and we go ahead and do the ring around the rosy. 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. I hope now that you get it. We're going to go ahead and move on and do a different example where we deal with calculating the number of protons, neutrons, electrons, filling out a Bohr diagram, and then doing the Lewis dot structure. So as in your notes, let's go ahead and look at sulfur. Sulfur has an atomic number of 16 and an atomic mass of 32. Number of protons is the same as the number of for the atomic number. So there are 16 protons, and since the number of neutrons is the atomic mass minus the atomic number, there should be also 16 neutrons. And since this is a neutral compound, there should be the same number of electrons as the number of protons. So you should have 16 electrons. So let's go ahead and fill this up. If you remember the first energy level can only hold 2 electrons. So I have 1, 2, okay? And the second energy level can hold a maximum of 8. So let's go ahead and put that in. So 1, 2, 3, 4, 5, 6, 7, 8. We currently have a total of 10 electrons. We have to fill out now the valence shell, the outermost shell. And we don't put the maximum amount, which is 18. We put however many is left. We have 16 electrons. We've already filled 10. So we need to fill 6 more. 1, 2, 3, 4, 5, 6. Now that I know how many electrons in the valence shell, there are 1, 2, 3, 4, 5, 6. I can now write my Lewis dot structure for sulfur. So I would start with the big S for the symbol, and then add 6. 1, 2, 3, 4, 5, 6. This is how you would do the Lewis dot structure for sulfur. Now that we've done this, you should be able to complete the rest of your notes for this section, and I will see you in class if you have any other questions.